Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Extended system.
Thank you, Jennifer. I realize that probably the audience that I'm speaking to here isn't quite the audience that this talk was originally written for, so I've kind of adapted it a bit. But I'm also not sure how much you know and how much you don't know, so please interrupt me. It doesn't matter if I get to the end of the talk or not. The main thing is that you understand something. With the building of quantum devices, the aim to build quantum computers and that kind of thing, there's been a lot more interest among theoretical physicists about quantum entanglement. Of course, we've always known that entanglement exists in quantum systems. We've accepted it, but most quantum mechanics textbooks that you read up to maybe 10 or 20 years ago really don't make any mention of entanglement in any important way, unless they're discussing Bell's inequality or something. Okay, but in recent times, it's been quite interesting to try to think about measures of entanglement entropy. If you've got an entangled quantum system, how entangled really is it? And that's what I'm going to be talking about today. And first of all, I have to make the disclaimer that I'm not a quantum information person at all, and I know very little. And I certainly know even less about quantum computing, so if there are any experts in that area in the audience, I must apologize. So let me start off by saying a few words about quantum entanglement. We're going to be thinking about a quantum system in a pure state, usually. And then we call that psi. That's some state in the Hilbert space of the whole system. And when the system's in a pure state, then the density matrix takes this very trivial form. We assume that there's some complete commuting set of observables in this system, and as in any talk on quantum information theory, there are always these two characters, Alice and Bob. And Alice can observe a subset A of the set of observables, and B and Bob can observe the complement. And of course, because the whole system is in a pure state, then in general, A's measurements of her part of the system she can observe are quantum entangled with those of B. Now, there are all sorts of different measures of the amount of the amount of entanglement, but one which has been proposed is the so-called entanglement entropy. And in order to that, we first of all work out the reduced density matrix of A, which means taking the full density matrix and tracing out the degrees of freedom in the part of the Hilbert space belonging to B. And then, once we've got this, computing what's called the von Neumann entropy minus trace rho log rho corresponding to rho A. And one thing that you can quite easily show, and if you get bored with the rest of the talk, you can prove this, that if Bob observes the complements of the observables of A, that is A union B, is a complete set of observables, then the entropy of A's reduced density matrix is the same as the entropy of B's. In fact, all the non-zero eigenvalues of row A and row B are the same. Now, I should say that... Okay.
What if A observes the empty set and B everything is, then one of the entropies trivial and the other is the full?
Well, if the Hilbert space belonging to A is zero-dimensional or is nothing, then I don't think this formula makes sense. I agree. Then basically, no, it will be true, but these two things will both be zero. There will be no entanglement.
Because row in one, so
in one case, rho will be 0, and the other case it will be 1, basically, and rho log rho would be the same. I think that makes sense, but I would actually have to think about that.
So should I think of A as A and B as Hilbert
Not
spaces?
exactly 1, it will be rho.
It will be rho. Yeah, it will be rho. So it will be 1, yeah. Yeah, but trace...
No, but rho is just a one dimension. The entropy would be 0 because it's...
Yeah, because it's pure.
It's pure.
because it's pure.
So should I think of A and B as Hilbert spaces or a set of observables? What is the trait?
You can think of them as you can think that the total Hilbert space is a direct sum of a Hilbert space A and a Hilbert space B, if you want. Think about it. Okay. So just a simple example. If we have two spin 1/2 degrees of freedom, of which A observes the left-hand one, B observes the right-hand one, and let's take this state, which of course is not the most general state. This is a 4-dimensional Hilbert space altogether. Okay? Then
You know, John, there are some
people here who wouldn't.
might not even know what a spin 1/2 degree of freedom.
Okay, it's a two-state system. So basically, the Hilbert space corresponding to A is a two-dimensional Hilbert space in which a basis is either called spin up or spin down. Okay, and the same for B. All right, so we're going to take a state which looks like that. Is that all right?
Yeah.
Okay. Fine. Do stop me when I say something which is not.
Well, it's just there's a spectrum of people here, but there are
Yeah,
some
sure.
students who probably,
Right.
you know, if you tell them C2, they'll be happy, but if you tell them spin 1/2, they
Okay.
whatever.
Okay. Now, so if you do the computation, which is very easy, you find that for this pure state, the entanglement entropy is this. And you see that if you have what we would all agree on as an unentangled state, just a product state between A and B, that would correspond, for example, to cosine theta equals 1, sine theta equals 0, then the entropy, the entanglement is 0. And you can also check, of course, that it's maximal if cosine squared theta equals 1/2 and sine squared theta equals 1/2, and then it takes the value log 2, and that corresponds to these what most people would agree on being maximally entangled states. So for this very special example, this seems like a reasonable measure of the amount or the degree of entanglement. And we're going to take it to be a reasonable measure then for much more complicated systems with a large number of degrees of freedom. But in fact, in this particular case, there's a theorem due to Bennett et al., who are of course well-known quantum information theorists that basically if we have m copies of this state and m is large, so this in general, when cosine squared theta is not 1/2, is a partially entangled state. So let's suppose that we have m copies of a partially entangled state. Then Alice can, by purely local operations, that means by making unitary transformations on her part of the Hilbert space, and also by classically communicating with Bob, that means just asking Bob, what did you observe when you did that? Then Alice can produce or generate, you can design a machine which would produce a smaller number of states which are, however, maximally entangled. And this may or may not be a good thing, depending on what you want to actually do with these states in terms of quantum, teleportation, or whatever. And the conversion ratio is asymptotically proportional to the entanglement entropy. Divided by, well, it's proportional to. So it's SA over log 2. Yeah. So this is one reason why it might be a useful measure, though I should stress that as far as I know, no one has generalized this kind of a result to things with a large number of qubits, which is what I'm going to talk about. So I'm going to talk about the case where the degrees of freedom of the quantum system are extended over some large region in RD with short-range interactions in between them. So we're going to think about a lattice quantum spin system. So spins again, but anyway, these quantum spins interacting with their nearest neighbors and so on, which it's known in certain limits called scaling limits are the same as an ultraviolet cutoff quantum field theory, though you don't need to know that in what I'm going to be talking about today. And then A is the set of degrees of freedom in some large subset of R, and the pure state that the system is in is the ground state of the lowest energy state of the Hamiltonian of this lattice quantum spin system. Okay? So let me just draw a picture. This is the whole region R. A observes this part of this region, B observes the rest, and we would like to understand how does the entanglement between these two parts of the system in different parts of space now depend on the geometry. Now, the first guess that you might make, because you've heard the words entropy here, and if you know much about entropy in statistical mechanics, you learn that entropy is extensive. That means it's proportional to the volume of the region in the limit where the volume gets large. It's an extensive quantity. But that guess is actually wrong, because in general, of course, we said that SA was the same as SB, and it's, of course, not in general true that the volume of A is the same as the volume of B. And, of course, then you might guess, well, what about the boundary between them, the surface area, or the D-1, or the D-dimensional generalization of that? And there have been a variety of papers over the years for looking at exactly solvable models of sort of coupled quantum oscillators or something, whereby you can actually check that that's true. Now, it's not in general true. When I give this talk to people who are more into field theory or even string theory, I better not say that too loud, they see entropy proportional to area, this must be a black hole or something. Well, this is absolutely nothing to do with black hole physics as far as I know.
England, they would say.
Yes, right. And just to make the point clear, this is in flat space. There is no, but there are no event horizons here. There is nothing general relativistic going on at all. Okay, but the entropy, nevertheless, for many models, although it's never been proved, and it would be very interesting to prove this, say, in 2 or 3 dimensions, that for an extended quantum system divided in this way, then the entropy is actually proportional to the area. So there's a challenge for you. Okay.
Sort of, it doesn't sound like probable because, it should depend. I mean, information can go somehow from A to B also through outsides.
Well, there's no outside. Okay, this is the whole universe, right? I mean, if there is an outside as well, then there is some entropy in that, and you can talk about that. But once there is an outside, once this is not the whole universe, then it's no longer true that SA is SB. Once you once you trace over the degrees of freedom of the rest of the universe, this is no longer true.
Could I, for example, think putting it on a sphere? Or
so this is really on a sphere, so I'm thinking, that this is really a sphere. But because once I draw it this way, then I have to say what's going on the boundary as well. So I'm really thinking about it being on a sphere.
So you say that you do believe this then in some large,
for all the cases that have been studied for D equals 2 or larger, which I'm going to be, but I'm going to be talking, in fact, about D equals 1, which is a bit more interesting. One thing that you see from this formula is because the entropy is dimensionless in the way I've defined it, because I'm choosing units where Boltzmann's constant is 1 or something. Then if this is an area, then it has to get divided by some length scale to the D minus 1. And in this quantum spin system, this would typically be the lattice spacing.
Why?
Or the mesh.
Couldn't it be the correlation?
It could be the correlation length, but it's not, actually. I mean, in the examples that one looks at, it's not. In the examples one looks at, there really is this strong dependence on the lattice spacing. There may be subleading terms here which do go like the correlation length and may be universal. But this one is not universal because it's clearly dependent on whether you choose a cubic lattice or whatever. So it's not this number C that comes outside here in this formula in higher dimensions. It appears to be not very interesting. So that's anyway. But it would be nice to actually prove this. Okay. But D equals 1 is different. And this tells you what we believe to be the case there, that as D goes to 1, you get a logarithm. And now, so in this case, we're now looking at a one-dimensional quantum system. And for simplicity, let's suppose A observes the degrees of freedom in a line segment of length L, and then B observes all the rest. It goes off to infinity or it comes around in a circle. It doesn't really matter. In that case, what one finds is, well, it depends on the correlation length. In general, so now we're looking at a quantum spin system, And in general, this has a finite correlation length, which means that the correlations between spins fall off exponentially with the distance, and in general, what one finds is in fact that the entanglement is sort of concentrated around a region, around these points, around these boundary points between B and A, as long as the correlation length is much, much less than the length of A. So as you might expect, most of the entanglement comes from there and there. And if we got more regions, it's just proportional to the number of boundary points between A and B. But then if we fix L and let the correlation length grow, that is, as we go to what's called a quantum critical point, then this entanglement grows, and ultimately it crosses over to this behavior where it depends logarithmically on the length. So now it's still not extensive, but it's depending logarithmically on the length.
You wouldn't expect something similar in 2 dimensions then?
So in higher dimensions,
replaced by something, by a correlation.
So in higher dimensions, this, going back here, this is the leading term, and C is pretty much independent of whether you're at the critical point or not. There may be other terms here.
I see.
Non-leading terms, which
have this
yeah.
more interesting behavior.
Yeah. This is very similar to what happens, for example, if you look at the free energy or close to the critical point or the specific heat, you get a sort of boring term with an analytic dependence on the temperature here, and then the interesting stuff is
lower order, which
it's further down.
Derivatives
Yeah, which by taking derivatives, which in this case wouldn't be a natural thing to actually do, I don't think.
You couldn't think of any reasonable thing with respect to which you might take a derivative, some kind of like a boundary field or something with respect to which you might take a derivative?
One of the things is that it's very hard to think about how you measure this entanglement entropy. In fact, this is, you can do it by doing quantum information experiments, but it's not at all related to the normal well, I'll talk a little bit more about that later, how it is related to the ordinary thermodynamic entropy, but it's not something that you can measure. In a finite temperature system, you can measure the entropy, you measure the heat capacity, and you integrate it up. But you can't do that here. So I know of no way of directly measuring it, so I know so derivatives, well, maybe. Okay. So these results have been checked in loads of cases. So this is a sort of summary of the literature up to now. But one of the most interesting suggestions was in fact made in a paper in about 93 by Wilczek. This is Wilczek of the Nobel Prize and these 2 other people, in which they showed, well, they were actually interested in black holes, but that word does come in their paper. But what they showed was that this number C is in fact universal. That is, it's independent of the details of the lattice and all of this. And in fact, it's related to this number little c, which is called the central charge of the quantum critical point that you're looking at. I'm not going to explain in this talk what the central charge is in other contexts. Let me just say that it's a number which characterizes whether your model is a Heisenberg spin chain or an Ising model spin chain, or different kinds of so-called universality classes. So it's one of these beautiful pure numbers such as Oded manages to calculate using ideas of SLE and so on. So yeah.
In finite size scaling, the central charge has to do with finite size scaling with periodic boundary conditions.
Yeah, yeah.
And so
And
so is that somehow related?
yes, and perhaps I'll get to a formula which will, and you'll see what the relation between those two things is, because C does actually relate to this, from the quantum point of view, relates to the low temperature behavior of the specific heat, and you can see how these two things relate. Okay, so now I'm going to talk about where these kind of results come from without actually doing much in the way of calculations. So this is the way that we have thought about this. Going back to these other papers, most of them involve actually taking an exactly solvable quantum spin chain and grinding through all the exact calculations. But there is a more general argument, which is the one that I'm going to try to give you here. So this relies on the path integral formulation of the quantum mechanics. So first of all, I said we were going to be at 0 temperature in a pure state, but just to make everything well defined, I'm actually going to start off at a finite temperature, 1 over beta, and I'm then at the end going to take the limit t goes to 0 or beta to infinity. So in that case, the system is described by what's called a thermal density matrix, in which the probability of it being in a state of energy E is proportional to e to the minus beta E. And the density matrix itself has this form here. So what these phi's and phi primes are, these represent, these label all the possible states of the whole system. So phi this is an eigenstate corresponding to a complete commuting set of observables for the whole system. This is a different eigenstate. These two things then label the rows and columns of the density matrix. And it was argued a long time ago by Feynman that there's what's called a path integral representation for this thing, which is given by the following very formal expression. That is, you sum over histories of the system. So now this phi represents all the degrees of freedom of the system, which we think as depending upon time, tau, and so we sum over all possible histories with the constraint that at time tau equals 0, the degrees of freedom take the value phi, and at time beta they take the value phi prime, and then we weight those paths, those histories, with this weight e to the minus s of beta, where this is what's called the Euclidean action of her theory. So mathematically, of course, except in the case of a free particle, where this is basically a inner integral corresponding to just ordinary Brownian motion. This is not a very well defined object mathematically. But at least it's much better defined than the ordinary Feynman path integral where you've got an I in there. So at least it's real. Okay, and then you divide this by the partition function, which guarantees the fact that the trace of the density matrix, that is when you put phi equals phi prime and you sum over all possibilities for phi, you get trace rho equals 1. So that's the kind of formal mathematical expression, but in pictures you can picture it sort of like this. So here's my one dimension, which I've called x, and now I've got a quantum spin system so I've actually got a lattice in x. So I've drawn it as a continuum, but you should imagine that at each point I've got a site of my lattice, but I do have continuous time, tau. This is actually imaginary time, but that doesn't really matter. It's continuous. So basically that formula that I wrote down for the density matrix here says that you do the path integral for the system over this surface here with initial conditions that the fields take or the degrees of freedom take the values phi here and phi prime here. And what the partition function is, basically corresponds to, is that you then sew the bottom edge to the top edge. So you then do the path integral on a cylinder of circumference beta. Okay? So from this pictorial point of view, it's quite easy to understand what it means to do the reduced density matrix. So remember, to get the reduced density matrix, we don't want to trace over all the degrees of freedom, but only those in the subset B. So that means that we take this surface and we sew it together along its top, and we sew the top edge to the bottom edge, but we leave open a slit along A. Okay, so the reduced density matrix is the path integral over this cylinder with a slit, and the values of the degrees of freedom above, just above and just below this slit label the rows and columns of my reduced density matrix. Okay, so that is row A. Now what we want to do is to work out trace row log row A, which seems to be a hard thing to do, but in statistical mechanics we often have to take averages of a logarithm, and there's a standard trick called the replica trick. That is instead of doing this, we take this to the nth power, where initially n is a positive integer, work this thing out, then we differentiate with respect to n at n equals 1, which certainly formally gives this. Now, the replica trick is used in random systems, etc., and it's not very well based. And indeed, in lots of well-known cases, it gives us the wrong answer. But this kind of replica trick is much better because we know a great deal about the spectrum of the density matrix. For example, we know that the trace of rho is equal to 1. And therefore, for n greater than 1, or the real part of n greater than 1, this defines an analytic function of n. So it can be then continued away from the integers towards n equals 1, and with a bit more argument you can prove that the right derivative of this at n equals 1 in fact gives you what you want. So mathematically, at least for a system with a finite number of degrees of freedom, this trick is a perfectly okay thing to do. Now, what does this mean? Taking the trace of row A to the n. Well, it means that we take n copies of this and we multiply them as matrices. And I told you that the rows and columns of the matrices are labeled by the values of the degrees of freedom above and below the slits. So what you should think is that you take n copies of this slit cylinder and you pile them one on top of the other, and then multiplying them as matrices means that you identify the degrees of freedom on the lower part of the slit on this sheet with the upper part on that sheet, and so on and so on and so on. And then taking the trace means that you identify this with this. Okay, so what you've then got is that you've got the path integral on this n-sheeted Riemann surface. Okay, well, that doesn't seem to make the problem very much easier, except in many cases for simple field theories, we know all about how to compute partition functions on n-sheeted Riemann surfaces. In fact, when we just have simple harmonic oscillators that correspond to what's called a Gaussian field theory, this partition function is nothing but the determinant of the Laplacian. It's related to the determinant of the Laplacian on this n-sheeted Riemann surface. And that's the sort of thing which has been studied by geometers for a long time, and there's a technique called the heat kernel regularization, because this thing does in fact need to be regularized. That gives one in fact an explicit formula for this. But I'm not going to go into the details of that because that's not quite appropriate. What I do want to do, though, is to talk a little bit. I told you that we're actually interested in zero temperature, but let's just see what this actually gives us at high temperatures.
You've got some other operator rather than the Laplacian. I mean, in the more general case.
In the more general case, it's the partition function of a conformal field theory on one of these things, which the point is that you know in that case that it's always proportional to C, the central charge. The partition function of any conformal field theory goes like something that's the size of the system to the power C with a coefficient which depends on the Riemann surface that you're looking at. Yeah, but these are all details which I don't want to, which I could explain. I mean, if someone were interested, and I do want to assure you that we did an honest, if not rigorous, calculation. In the high temperature limit. So let's I've been talking about this von Neumann entropy, and it would be nice to understand how it relates to the entropy that we usually think about when we learn about statistical mechanics. So let's look in the high temperature limit. That means that the radius or the circumference of this cylinder is very, very small as compared with its length. So this picture was a bit hard to draw, but basically what you've got here is that in this region here, you've got this slit, and this cylinder wraps around n times in this place. So along this interval, you've got a cylinder of circumference n times beta and length small l. And in the other part, you've got n copies of a cylinder of length total L minus L, but just going around once. And in this limit, when it becomes almost one-dimensional, you would guess, and in fact you can prove in many cases, that the partition function approximately factorizes into a piece corresponding to here, which is this bit of length small l, but wrapping around n times beta times the rest, which is this. Also, one knows that in this limit, well, this is basically saying that the free energy is extensive. That is, the partition function goes exponentially with the size of the system, which in this case is L, times a function which we call beta times f beta, which an f of beta depends on the system that we're talking about. So if you plug this approximate formula into here, you get this rather complicated expression for the trace of rho a to the n. But the nice thing is now that if you differentiate now this with respect to n at n equals 1, what you find is this formula here, and then you can rewrite this in terms of f, which is beta times little f, and e, which is the derivative of that with respect to beta. And this is the standard statistical mechanics formula relating the thermodynamic entropy, the free energy, and the internal energy. So all I've shown you is this definition for the von Neumann entropy, the entropy of entanglement. If we apply it to a thermal state, we get the ordinary entropy. Okay. Now I'm going to look. This could be applied, by the way, in higher dimensions as well. But now I'm going to suppose that our one-dimensional spin system is at a quantum critical point, and a special kind with what's called a linear dispersion relation. That means that it's basically many such quantum critical points have this property. And then actually we know how the free energy at finite temperature depends on the temperature, because it's basically just given by dimensional analysis. In fact, this is just the version, this is the one-dimensional version of what's called Stefan's law for black-body radiation. So in 3 dimensions, we have photons whizzing around at finite temperature. We can work in units where the velocity of light is 1 and h bar equals 1, and then everything determines then that the free energy in that case goes like 1 over beta to the 4th, goes like t to the 4th. This is the well-known Stefan's law of black body radiation. If you do that same calculation in 1 dimension, you find that it goes like t squared rather than t to the 4th. The only thing that you can't work out from that formula is the constant, but when you do it, it turns magically to be related once again to this universal number c. And for a photon with no polarization or whatever, it will be 1. So just a boson. So just applying that formula that I had here, to the case where we do know f of beta, this is what you get. Okay, well, that's fine. It just tells you quite a lot about the density matrix, but at finite temperature. And this is going to be valid, as I said before, for L much bigger than beta. But in one dimension, we have the power of what's called conformal symmetry. That is, we can actually take this cylinder and conformally map it to the plane. Okay? So whoops, what happened? We do this by a logarithmic conformal transformation, and that means that something which decays exponentially along the cylinder decays as a power law in the plane. So in fact, what you find then in the plane, and what does the plane correspond to? That corresponds to taking the circumference of the cylinder to infinity. That's beta to infinity. That means temperature to 0, and it tells us that for this quantity, for this quantity, it's going to decay as a power law at t equals 0, and now we take this formula, differentiate it with respect to n at n equals 1, and that's what we get. So the logarithm comes from this. Okay, now, so that's basically where this result comes from, although I should stress that we did a much better job, or a more systematic job on deriving this. But as well as this, you can actually sort of go halfway. You can also look at the case where L is of the same order as beta, and when you do this, you get this rather nice looking formula which actually captures the crossover between the 0 temperature von Neumann entropy and the thermodynamic entropy. Because if you take the limit beta goes to infinity, here, that's t goes to 0, you get back to this formula here. On the other hand, if you look in the opposite limit where L is much bigger than beta, and you work this thing out, because this goes then exponentially, and you take its logarithm, then you find that in that limit the entropy is indeed extensive in L with the right dependence on T. So this is the way that this 0 temperature von Neumann entropy, which is not extensive, crosses over into something which is extensive. Though I should stress that from the quantum information point of view, only the 0 temperature limit is a relevant measure of entanglement. If you are at finite temperature in a mixed state, then this entropy, it's been shown, is not a particularly useful measure of entanglement. And in fact, the useful measures which have been proposed to discuss mixed states seem to be much too hard to compute analytically. So that's unfortunate. Okay, so I've got a few minutes left.
Oh, yeah.
Yeah, I've got tons of time. Maybe I think I've been going way too fast, and I've lost almost everybody. So because I'm going to talk about a slightly different subject, maybe I should ask any questions, and don't be at all embarrassed if you... Okay, well, if you're really embarrassed, you can ask them afterwards in private. Okay.
So do you only expect this, I mean, the central charge connection will clearly only hold if you have this critical point.
Oh, at a critical point.
So, but what if you're not at the critical point?
Okay, so if you're not at the critical point. Basically, because this is a logarithm, you know, and the only way, so when you have a finite but large correlation length, all that can happen is that this log L gets replaced by the logarithm of the correlation length. But when they are of the same order, when the correlation length and the L are of the same order, then there's going to be some additional function of indeed L over psi. And that function will be universal as well, but depend on the model. And in fact, for the Ising model, for the transverse Ising model, we computed we computed this function exactly. But in general.
What if you have a model which has a first order function?
If you have a model, well, then you have no diverging correlation length, as you know. So presumably what actually happens is that as you approach the first order transition, this thing grows, and it grows up to a maximum. But then, yeah. It would saturate. I don't know of any explicit calculation of that. So as long as L is much bigger than the correlation length at Tc, then the entropy is going to be constant. Yeah. That would be my guess. But then whether the coefficient outside there is in any sense universal, things tend not to be universal at first order transitions, but that would be interesting. I don't know the answer to that. One would expect, you know, the kind of thing that you were interested in, as in the Q state Potts model, as Q approaches 4 from above, then this would show some interesting kind of behavior. Any more? Okay, so now I'm going to go to a slightly different or related question, which is, how does this entanglement entropy depend upon time? This is kind of interesting because nowadays we can prepare these quantum systems at extremely low temperature. We can look at these cold atom traps and that kind of thing, and we can actually prepare them in a well-defined quantum state. We can then let them evolve according to the laws of quantum mechanics without any interference with the environment, at least approximately. And then we can ask, okay, so for example, if we prepare it in an unentangled state, that is where A is not entangled with B, or a slightly entangled state, and then we evolve it with this Hamiltonian of the entire system, how does this entanglement entropy depend upon T? And the first thing to realize is that if A were the whole system, then of course then the entropy would not change. It would still be either 1 or 0. But this operation of taking the partial trace, the reduced density matrix, does not commute with the Hamiltonian if A is interacting with B. So
does this give you some measure of like the errors in the system that are building up over time or not?
Well, I think that's, I don't know the answer to that. I mean, this is what one would like to say, but it's not been.
We would want to look, for example, what happens if you start with a perfectly entangled pair, then let it evolve, because it will lose
some of the, right, whether you lose the results of the calculation if you, right, so that would be.
Well, all we're doing is, I mean, it doesn't, this calculation, actually, this calculation that I'm going to show you doesn't assume that the state is in fact unentangled. It just assumes that the state that we start from is not an eigenstate of the Hamiltonian. And as you'll see, there are some further assumptions that the average energy of this state is well above the ground state. Okay, but you'll see that in a moment. So we can calculate this from the path integral point of view in the same way, and this is what I've tried to illustrate here. So this is once again a picture of the way the path integral would calculate the density matrix. So basically, we start from this given initial state, phi 0. We evolve for time t, and then we obtain a state which is represented by the values of the degrees of freedom just below the real axis there. And then, in order to work out, so that gives us the state, that gives us the ket state, but in order, or the bra state, but in order to get the ket state, we've then got to start here and evolve for a time t going down there. And then to take the trace of the density matrix, we sew along here. And to take the partial trace, we sew along here, but with, once again, a slit along A. So basically, the time-dependent density matrix is given by the path integral over this surface here with given values of the fields of the degrees of freedom here and here with a slit here. And then, once again, because we want the entanglement entropy, we're going to take the nth power of this. That is, we're going to take n of these sheets, and we're going to sew them together in the way I indicated previously. So now we've got the path integral on an n-sheeted surface, but now with a boundary along here and a boundary along there. But one can apply the same kinds of methods.
There's one thing I don't understand, because you before also introduced your temperature and had a path integral its imaginary time direction.
Yeah. Okay, so this is very tricky. What you actually have to do is do this first in imaginary time and then analytically continue to real time.
Then take
if you wanted to do the finite temperature, though, you'd only analytically continue part of it.
Part of it, yeah.
Okay.
Yeah.
So then it will be very hard to have an image what that means when you now conformally map it.
Oh, well, what you have to do is that you do all these calculations with a tau 1 and a tau 2 here, okay, which are initially in imaginary time, and then you calculate this using your conformal mapping, blah, 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 and then you analytically continue the result in tau 1 goes to t, goes to it, tau 2 goes to minus it.
Plus beta.
Yes. Yeah. So that's how these calculations are actually done.
You don't anticipate any problem. I mean.
Well, there is a problem which I've swept under the rug, which does come and hit you, which is that you do have to retain a small. Okay.
I mean, I'm not talking about a rigorous problem. I'm talking.
No.
Yeah.
There's a real problem, which
Real problem.
which actually hits you,
Well, you know,
which is that you have to do so that's what you want to actually work out, and what you have to work out is that is you have to introduce an I epsilon prescription.
So get a principal.
But the final answer depends weakly on epsilon. So you can't let epsilon go away at the high end, and I'll show you in a moment. Okay? So let's, okay. So let me just go on. So these are the results. Okay, so there is this beta effective. So let me explain what that is. Okay, so this state that we start from is not the ground state, and so has some typical energy above the ground state, and that defines a characteristic temperature, and that's this temperature here. Okay. So beta effective is basically.
And that's why you say you have to remain above. That this isn't true for the ground state. That you have to be above the ground state.
And in fact, the energy above the ground state has to be extensive.
Right.
Okay. All right. So when you do that, in that limit, however, I can now take this as small as I want, as long as I don't take it to 0. And as long as so this gives me a length scale, and if the times and the lengths are much larger than that, what I get is that the entropy increases with time. The entanglement entropy increases linearly with time, up to a point T equals L over 2, when it saturates to the thermodynamic value.
Wait, now something I don't understand. What if you had started with a maximally entangled state?
If I'd well, that would be starting with a state which is very close to the ground state. I mean, is that what you mean? Maximally entangled?
Well, maximal entropy. I mean, you start with the one which has maximal entropy.
SA.
Which has maximal SA.
Yeah.
That does not necessarily.
That would be the one where we had a pure state, where we started from a pure state which was the ground state, and that would then not evolve. Nothing would actually happen.
I see. It doesn't lose its integrity.
No, it doesn't lose its. No.
Yeah.
Is the L over 2 coming because you have, I mean, you're basically...
I'm going to explain that in a moment.
Quasi-particles that are...
Quasi-particles, good. That's the next
But this is somehow
next picture.
One would expect that it's, that you are somehow, the coherence is destroying your entanglement somehow.
Yes.
You start with a, maximally entangled state, and you should lose it somehow.
No, if you're, yes, I mean, you would expect that if you're in contact with a reservoir or a heat bath, but if you just unitarily evolve this system in its ground state, in this maximally entangled state, then nothing happens unless it's in contact with an environment, which would then destroy the...
This simply corresponds
which
to
would be...
Neumann entropy is constant in time.
Yes, yes, right. So what would be a very interesting question, and one that we might answer in the future, is if you put this thing in contact with some kind of a heat bath, an environment in some case, then what actually happens? And we actually have looked at the case where you take two systems, two semi-infinite systems, each of which is in its ground state, and they're not entangled by definition. They're not coupled, and you couple them together and you see how the entanglement between these two systems grows. So that's probably not quite the question that you... In that case, it doesn't grow like T, it grows like log T.
So, and the maximum versus ends up, how large is that compared to the maximal SA?
That is maximal, right?
There's no maximum. I mean, this is a very large system. I mean, the maximal SA, oh yes, it will be. For a quantum spin system, there will be some maximal something that it could possibly be, but it's always smaller than this. Yeah.
Right, it's just gone up to the maximum, to its theoretical maximum, and it just...
Yeah. Yes.
Yeah.
No, it's not gone up.
Well,
This is much smaller than the theoretical maximum.
this depends on the state that you started with. So I can make this as large as possible by making beta effective small. That is, starting from a state which is very, very, very high temperature. I mean, I hate to say that the temperature of this state, because it's not a thermal state that I'm starting from, it's a pure state.
Right.
But it has a characteristic energy which gives us a characteristic temperature.
That can't be, because you just convinced me that this spin system
If you took an extensive...
A spin system would, yeah. Okay, so we're looking at a spin system in the limit here where the fact that we have a maximum energy state, that the entropy turns over, we're not looking at that part of it in this approximation. I mean, it would be very interesting to actually do that as well. Yeah. Okay, so somebody suggested there whether this turnover was something to do with quasi-particles, and it basically, yes, you can get that picture here. So basically what is happening is that this initial state, it's a high temperature state, and it acts as a source at some effective temperature. Okay, so this is a picture this is a space-time picture. Okay, so this is space along here, this is real time now. And the point is that at t equals 0, you've got this state here, and then each point here, each lattice site, is acting as a source of left-moving and right-moving particles. And in this approximation that we're looking at, where we can represent it by a field theory, these things travel in straight lines at the speed of light, or the speed of whatever your quasi-particle excitations are in your system. So I call them photons. They don't have to be photons. They could be phonons or electrons or whatever. And the assumption, if you make the assumption that the left and right moving photons that originate from the same point are entangled, but because this is like an incoherent source between different points, the ones that come from different points are not entangled, then you can see that the origin of the entanglement between A and B is due precisely to those pairs of left and right moving photons, such as the one I have drawn there, where they originate from a source here where the left moving photon hits A and the right moving photon hits B. And then you can see that for small times this is then going to grow linearly in t up to a point, in fact, where in fact t equals L over 2. And for larger times, every point in A is going to be entangled with a point in B, so it's going to saturate. So this is a very simple physical picture, but quite amazingly, we then did calculations for the transverse Ising model, where you can do all of this thing explicitly, where first of all you have a lattice, so you have a lattice dispersion relation, so some particles actually don't travel at the speed of light. There are some particles travel less than the speed of light, less than in the light cone, within the light cone because of the effects of the lattice. And you can also do it away from the critical point.
So you're taking z not necessarily equal to 1.
Well, z is 1 still, but the dispersion relation, the lattice dispersion relation looks like this, so that these particles, the group velocity it is
step
these particles travel at the speed of light, as it were, but these particles don't. They travel more slowly. And we also did it for a non-critical model with a gap. So then the dispersion relation looks like this, and these particles travel the fastest. Anyway, and no, not in the Ising model. Do you mean, does it come down again? No, that's the edge of the... No, when you transform the Ising model into free fermions, it's just inside this real zone.
Yes, the Ising models.
So these aren't really free fermions, it's just the Ising model. Anyway, that's another point. The nice thing is, with all these different things, this picture then gets slightly modified, and the entanglement entropy still grows linearly, but it doesn't saturate immediately. So what you get is, versus T, the entanglement entropy grows up to the point T equals L/2 when the fastest moving particles arrive, and then it curves over in general. And this curving over is due to the fact that not all the particles are traveling at the same speed. But you can actually, this picture, you can do calculations based on this picture, and it agrees exactly with what you find by the exact solution of the model. So it was a nice verification of this particle picture. But one should note that this entropy does not always increase. So you might have thought, oh, well, we all know that the entropy would increase because we were taught that entropy increases. But this kind of entropy can also go down again. And in fact, if you look at the case where you've got a whole bunch of intervals, and you look back at this kind of a picture here, then there are going to be some points where these intervals are kind of in phase, and in other points where they're actually out of phase. So in general, this entanglement entropy, in this particular case, in fact, when you've got an infinite array, this entanglement entropy oscillates forever. So I haven't a clue what that means physically, but it's an interesting result. And whether, this will be something that will be useful or not, I have no idea. So let me just summarize. This quantity called the entanglement entropy, which for systems with just a finite number of degrees of freedom is certainly a useful measure of entanglement. Whether it is for others remains to be seen. However, it can be computed using results, either using results based on exactly solvable models or for field theory, for many extended one-dimensional systems. In general, away from the critical point, it's proportional to the number of boundary points, basically, between A and B, but this coefficient gets logarithmically large near a quantum critical point. We can understand its crossover to the more familiar thermodynamic entropy, and it shows this interesting time dependence under unitary evolution. There are lots of other measures of entanglement which have been proposed. For example, there is something called the concurrence, which really is related in a spin chain to looking at various properties of the spin-spin correlation functions. There is something for a mixed state called entropy of formation, which I referred to earlier, which is this thing which is extremely hard to think about computing analytically because it involves an algorithm which involves maximizing over all possible ways that you actually do this operation, which even numerically is extremely hard to actually do for a large system. And finally, this result that I referred to in higher dimensions, that it really is proportional to the area, that seems something which is probably capable of actually rigorous proof. So thank you. I'll stop there. Fine, thank you.